Okay, so hello everyone. Welcome to this special talk today. Our speaker for today is Professor Dr. Imran Anwar. Most of you already know, I think, but I would like to say a few things about him before he starts. So Imran Anwar has got his PhD from the Abdul Salam School of Mathematical Sciences in Lahore, where he specialized in commutative algebra. And then he moved to ComStats, where he worked as assistant professor for some time. And then he came back to the Salam School of Mathematical Sciences, where he worked as a shared professor. And currently he's a shared professor at Department of Mathematics at LUMS, where he has been chairing the mathematics department since 2021, as far I remember correctly. Imran Anwar has done a very great job to internationalize the mathematics atmosphere in Pakistan. For instance, over previous years, he has organized many SIMPA conferences in Lahore. And currently, he's also hosting this International Mathematics Master Program in LUMS, which has been very successful so far. And beside this, to improve the mathematics education in primary level, he has this interesting idea of math circles, where he is very actively organizing these activities in different primary schools. So certainly it's a lot of efforts to do all these things, but we have him here today, and we wrote to him to give a talk on the history of maths, and we are really happy that he agreed beside of this busy schedule. So he would like to talk about building into some overriding problems in mathematics. So please, Imran, you're free to speak.
Thank you very much, Faisal. Thank you, Wajid, and thank you the whole organizing team for inviting me. And this is quite a kind of a privilege to have a gathering of youngsters whenever we talk. That is the one thing which is really very exciting. And youngsters who really would like to learn mathematics, and I always trying to adopt an informal way. So this talk it will be quite informal, and this is a kind of a math talk which starts with a story. Okay, there's a story of three fish. The two young fish are swimming along. They came along an older fish who were moving in an opposite direction. The older fish stopped and nodded the young fish and said, "Good morning, boys. How's the water?" And the two fish swim for a bit, then eventually stop. And one of the younger fish look at the other. What the hell is water? Okay. This is an excerpt from one of the famous commencement speech in the US history by David Foster Wallace. If you got the time, just do Google and search. You will find a video. This is a very, very good talk and better than mine. David Foster Wallace. And what is this? What is the moral of this particular story? Let's focus on it. The immediate point of the story is that the most obvious, ubiquitous, important realities are often the ones that are hardest to see and talk about. And that particular thing. The story was quite cute, short, small, but the task is quite huge. So in mathematical world, the most obvious or clearly thing is the most hardest thing. And mathematics, when we talk about the thinking process, when we talk about how to think, how to envisage any particular thing, mathematics has an empirical importance there. So let's talk about a little bit how mathematics involve into the thinking process. So I think every one of you, whenever we talk about philosophy and how to think, how to see, All these things start from definitely the Socrates and his students. And the most important student of Socrates is Aristotle, who learned a lot from Socrates and wrote a book. And particularly, the most important message from that particular book is that logic is a tool to think. So if you are going to think about any particular thing, so you can take logic as a tool, and the title of his work, the book he has written, the persons who are working in philosophy, they call it organons. Organons, basically, this particular area of thinking and logic is being taught to lawyers as well, and it involves a lot of mathematical logics. Then the second person who came into the story is René Descartes. And René Descartes, you know him due to his mathematical work, Cartesian plane. But René Descartes come to his this particular question that how to think mathematically, what should be the rules for the direction of the mind, how to think scientifically. So he raised this particular question, and he has written this particular book of rules for the direction of mind, which was an unfinished work, his territories, and you can Google it. You can find there are multiple thoughts on it. And you know what, Rene Descartes, I think the most important work he has done has given an idea of a universe, hypothetical universe, which he called the Mathesis Universalis, is a hypothetical universe which is modeled on mathematics. And later on, after Descartes, Leibniz took this up, and many mathematicians of the 16th and 17th century, they were trying to understand the scientific process, the thinking scientific process mathematically by following the same history, Mathesis Universalis, which was an unfinished work by René Descartes. And now come to the real business. The last person, the third person, is George Boole. I think the computer science persons, and you might heard of Boolean algebra. So what George Boole did, he mathematicalized the whole thinking process of the Aristotle, and took the philosophy from René Descartes, and he has written a book which is called The Law of Thoughts. So everything in this particular picture is completely philosophical, looks quite abstract. And but to be very honest, this philosophical thinking led to revolutionize our and impacted the whole modern era. So we are living in the era of information, and this is due to the work of these three men. And very less is being discussed and told about George Boole. He was an English mathematician, and he basically he mathematicalized the whole thinking organelles into a mathematical language. And the philosophy he adopted is, for any particular question, for any particular thought, use logic as a tool, and take a particular question to go under, over, and beyond. By the way, George Bull has a lot of connection with Pakistan too. Very few people knows. You might know about Mount Everest, which is the highest peak. It is named after Mount Everest. I think his name is exactly Everest, Lord Mount Everest. He was his father-in-law. So George Bull was married to the daughter of Lord Mountbatten, and what was okay, and like many mathematicians, many celebrated personality, he was an unorthodox genius who was largely self-taught, and he got a key position, and he was a very dedicated teacher. This is quite strange. You don't have to be taught in a school or university to be a very good teacher. So just like George Poole. So okay, we talk too much serious thing. So whenever you are going to study something, this is really important to fill your pocket with enticing quotation. So let's take first advice from George Poole. George Poole says that the general law of nature are not immediate. This is many people argue about that everything is trivial. So one can look there, one can look there. Everything is trivial. So George Boole warned that nothing is so trivial. It is not immediate object of perception. So if you would like to understand any natural phenomena, you have to be patient. The second person is a Nobel laureate, Richard Feynman. And if we talk about calculus teaching, so he's the biggest giant who has tell us how not to teach calculus. So, if one people talk about the advices, so everyone says that one should do that, one should do that. Those kind of advices are stacked and skyscraper. But I think the most important advices are one should not do that. So he's the one who gave these kind of advices to those who do not know mathematics. According to Feynman, if you don't know mathematics, so it is you are blind. You can't see the beauty of the nature. You can't understand the nature. So I think I'm sorry for those who really don't understand mathematics. So they are living a blind life. Okay, both of these persons are quite dedicated mathematicians, but their wives were not so happy with them. So let's firstly talk about Feynman's wife. So she complained for a divorce, and what was written in the divorce complaint I am writing. So I have written it here. So I'm just reading it in the wording of her wife in the complaint. He begins working of calculus problem. Is bad as soon as he awakens. He did calculus while driving his car, while sitting in the living room, and while lying in the bed at night. So that's why she wanted to leave her. So this happens with mathematician. George Boole, who taught us logic, he failed to teach logic to his wife. So in late 1864, so he was going to take his classes, and there was heavy rain in the during the winter. So he was very dedicated. It shows his dedication that uh, he, I think he covered a distance of 3 miles by walking, and he wet himself in the rain. And later on, he developed a pneumonia. Now, here comes his wife in the story. So, causation was a strongly believed theory at that particular time. So, in the medical history, I think even till date, many people believe that the cause that make you sick, that same cause will make you cure. So his wife was a strong believer of that. So because it was wetness which brought him the disease, so his wife wrapped him in a wet blanket so that he can get. He was always already suffering with pneumonia that got worsened, and ultimately the poor guy died of pneumonia. So I don't know. So sometimes this is really hard to teach logic to your wife. So that can be seen in the George Bull's case. Okay, the person who is the father of logic, but he died poorly. Anyways, let's move to okay. We talked about serious empirical thing, mathematics role, everything, and we talk about something about the goofy wife and interesting quote. Let's go to the promise. What I have made, I will expose you some interesting problem. So okay, this first problem is quite simple looking that you start from here. If you have an n by n grid, and you start from here, you have to go here, and the grid is n by n. The rule is that you should not cross the diagonal. So this is one path, this is the second path, this is the third path. The question is how many such paths are possible? So this is the first question. Okay. Second question is this one. Triangulation is a very, very important tool in topology. We know it because of Euler. Euler wanted to do the triangulation, but even before, well before Euler, the Greeks were doing the triangulation. You know what is the magic of triangulation? If you do triangulate up any n gone, n plus 2 gone, so you can calculate the sum of the interior angle in a blink. And for instance, this is a hexagon, and I triangulate the whole region. I just count the triangle 1, 2, 3, 4. You know what is the sum of the interior of the triangle is 180. 4 multiplied by 180, that is the sum of the interior angle. First time the Greeks were doing so, and later on our triangulation, we use triangulation in topology in order to calculate homologies and cohomologies because it gives the structure of the simplicial complex, and simplicial homologies are easy to build. So triangulation is a very, very important tool in topology. For Greeks, they were very well, but there is a question which is enumerative associated to the triangulation. If you have an n plus 2 gone, in how many ways I can triangulate it? This is a second question, which is quite a combinatorial question. Okay. So I try to cover where triangulation can come into. I know there are numerical people who are interested in triangulation to triangulate a particular region and to apply some migration processes. Okay, then the third problem, which is apparently easier than the previous two. Uh, it says that, for instance, you are given with a 5 pair of parentheses. In how many ways you can write it so that it does make sense? So lattice, don't show an error with the middle bracket. You understand? Whenever you open a bracket, you have to close it. In how many ways you can put a pair of parentheses. So you are given one pair, so there is only one case. So with 2 pairs, so there are only 2 ways. So with 5 ways. Okay, so these are three basic kind of combinatorial problems. Now the question is, the first problem you have seen the grid problem. The second one was the triangulation problem. The third one is this parenthesis problem. Is there any relationship between these three problems? Apparently, completely different scenario, completely different looking problem. Here is a surprise. They're the same. They gave the same count. This is the power of enumerative combinatorics. Combinatorics is a very, very enumerative combinatorics is a very, very strong tool. And sometimes these easy looking problems lead to a very important discoveries. And by the way, the sequence which shows up, if one would like to try, this is a habit of mathematician. If they see something, they try it for one case, for two, for three. If anyone is interested to verify, so the sequence goes like that. And by the way, this end term, general term, is computed in this particular way. I'm not going to show you the generating function, but you might be interested what is important about this particular sequence. The way the sequence is known as a Catalan sequence, Eugene Catalan, named after, but it is not Catalan who came up with this particular problem. So it is our friend Leonard Euler in the 18th century who came up with this particular problem. What I mentioned that if you are given with n plus 2 gone, in how many ways you can triangulate? Because whenever in the history triangulation comes, I do understand that the Greeks were the first one who were trying to understand the sum of the interior angle, the rigid geometry, but it was basically the Euler who popularized the triangulation. And he raised this particular question that in how many ways I can triangulate an n plus 2 god. And basically, the whole theory was started by Euler. And Eugene Kaplan, he was trying to understand the problem of Tower of Hanoi puzzle. Uh, I, I will discuss this problem once again in forthcoming slide. But the story starts from basically the Euler. Euler is the one who introduced this particular idea. And number, everyone is familiar about the Fibonacci sequences and then the golden ratio. And there are lots of myth and there are strong believer that Fibonacci sequences and golden ratios exist in nature everywhere. But uh, through this particular talk, I'm going to give you a message that unfortunately Fibonacci sequences has lost their place. Now it is believed that Catalan number are almost everywhere. Catalan numbers are wonderfully ubiquitous. They appear in the variety of disguises. Catalan numbers have a rich history, and the people discover it in a different way. There is, I will show you. Okay, these are the two books. So where Catalan number is being. So this is in my office, but I don't have this book. Now Catalan number has enormous application because with the rise of computer era, let me just tell you again, the second good news for mathematician is that with the AI importance, with the ML thing, you know what, the importance in computer science, now it is driving toward theoretical computer science and theoretical computer. So all the researchers are working on the more on theoretical basis because coding era is almost finished. People don't need coder, and I think every one of you might understand that even if someone doesn't know about the coding, and if one would like to write a Python code, one has to give a good prompt to your AI, and AI can help you to write a code. And to be very honest, I'm saying it safely because I tried it. I never tried epicycles. I would like to do something with epicycles, so I just give a prompt, and the code works really well. I don't have to think much. So somehow coding era is finished. So with the rise of AI, the importance of theoretical computer science has been elevated. So in theoretical computer science, what people work is to understanding the patterns. In understanding the patterns, the most important tool is enumerative combinatorics. And by the way, half century ago, combinatorics was not considered to be a subject of importance. You don't find someone who said that I am going to do PhD in enumerative combinatorics or something. So, though this particular subject was introduced by Euler, people do work on graph theory and this kind of thing, but not the combinatorics of the number, looking at the patterns, finding the generating function, and these kind of things. And by the way, these kind of studies exist almost in all branches of mathematics and physics. People in physics are trying to understand a particular pattern. They arrive to a new patterns of number sequences, and now there's a boom to this particular area since the enumerative combinatorics have been transformed into a rich area of research now, and now this is a very fastly growing area. Let me just mention that the last field medalists have one person from this particular area, John Hu. We have two Abel Prize winner, Lovash and Victorson. So Lovash and Victorson, they are the one who are working in this particular area, and now John who also is from the same area. And one connection to enumerative combinatorics, I think those who are interested in the big problem in math, so P versus NP is related to is a foray to enumerative combinatorics, and then one question in computing world is the quantum supremacy, quantum computing, quantum world. So whether quantum computers can solve P versus NP problem or not, easier world. And that particular study has been led by the one who are working in this particular area. And someone are interested to get more detail on the graduate text. Uh, it is written by Richard Stanley, who is a professor at MIT, and these are the two books, Innovative Combinatorics. And those who are interested in the application side, so this is the best book, Analytic Combinatorics by Flogelet and Tajvik. And this work, by the way, this book is mostly studied by computer science person, not by mathematician. And they found a lot of application in the computer science, and this area is growing exponentially now. Okay, now this is because this was my area now, enumerative. So I started with commutative algebra, then I moved to some problem in enumerative combinatorics now. So commutative algebra people are also working in enumerative combinatorics as well. So now I move to the topic from the history. So definitely every one of you already know that basically the recorded mathematical history is found in the tablets we found. So it started in 2000 BC, and where people were trying to understand the table. So they were just writing the multiplication table. And let me enlighten you that Babylonians were not aware of division. It came quite late. And now, the main thing which was important, I think, which played a very important role uh, for mathematics is Alexander of the Great. So when his expeditions were happening, so during the same time, the Persian Empire was set up, and in the Egypt and in this part of in Iraq, so there were libraries and there were big institutes set up where which is known as Alexandria Library, and Ptolemy school of thought were there, were trying to understand the mysteries of the universe, how the solar system works, and these kind of things. So they were developing mathematics, and Persian Empire played a very important role, but I think the most important role was played by Alexandrov at that time. That's why the library, the big library of the ancient Greek is named after Alexandrov. So this is the Library of Alexandria. And do you know what happened there? So with the rise of Christianity, uh, the whole during that particular time, so the most importance was given to understanding the abstract concepts. So people were trying to understand the paradoxes. Zeno was there, and Eudoxus of Cnidus was there. They were trying to understand the number system. So there were lots of problems which were hardcore mathematical problems they were trying to understand. But then Roman came, and Roman expanded, and Roman knows only one thing: to fight and kill and invade. And they have no value for sciences. They have no value for, particularly for pure mathematics, I must say, because applied was there. I will show you. They love applied mathematics. But this is strongly believed by the mathematical society that the way they ruin the Alexandria library and out of hatred toward the pure mathematics, that dent mathematics a lot. And from there, the dark era of Europe got started. Uh, eh, okay, this is about the Alexandrov. So this particular period, if you would like to explore more, this is called Hellenistic period. So when Alexander died, so new state emerged, and there emerges new libraries. People started exploring more questions. Okay, mathematics has been a subject for rituals. So in Hinduism, their rituals, so whenever they have to perform a ritual, I think what we have seen in the movies as well, so they use to build fire altars. And there are some sutras which was written in the sense that if you have one kind of prayer, for instance, if there is someone died in the family and they need to set a worship for altar for his or her blessing, and similarly, if someone buy a new house and they are seeking the blessing, if they are marriage ceremony, so they're in every different prayer, they need to build a fire altar. And fire altar, so what they used to do, so the fire altar building need to be quite accurate. They involve the sides, north, east, west, south, and the precision and accuracy was at the peak. And what they use the rope and the nails. And this kind of construction, geometric construction, they call it Sulbasutras. Sulba means the rope, and sutra means the method to construct. So, by the way, in the Indian history, you don't, in the Vedic history, you don't find any discussion of pi, because if you are constructing a circle, if you are your tool of geometry is the rope and nail, so definitely you can measure the circumference quite easily by using the rope. And that's why not much history quest was there. But it is very surprising if even if today I ask you, you have a rope and you have to build a perfect square. This is the method this was given in the Sulbasutras. So that you have to, okay, so if you have a line, you can divide it, then you can use the rope to a circle. Now, if you have a circle, so you have this particular line. So with the help of line and the rope, you can construct a perfect square. And by the way, they use this particular thing in the Sulba Sutras. There are proof givens. And this is a very, very interesting proof. So this is the proof of can you construct a circle? Okay, even if today, can you construct a circle of equal area of a given square? So this is something is doable, and it is not squaring the circle. This is the other way around. And the first proof of this one was given in the Sulbasutras, and this is a proof. And the method is you just draw A, B, C, D. You draw it like that. Make a line X, Y, Z, the bisector of this particular thing. Then mark Z, which is the 1/3 of it, and draw a circle. And this particular circle is basically having the same area as that of your square. And by the way, the persons who have written these sutras definitely in Hindu don't claim that this came from the heaven or something. It is written by the persons. Mostly, uh, I think now this is the part which is in KP, some region, and some region in Punjab as well. Mostly, Lahore is very, very sacred to Hinduism. I let me tell you that because many sutras and many Vedas have been written in this particular land. And the persons who have written is Budhyana and Apastamba. So they have, if you leave their worship side, so mathematical side is quite beautiful. It's very, very enriching. Very, very enriching. Okay. Then there are certain questions, I think, which was discussed in the Vedas. I think no religion is free of this particular question, and definitely, if we talk about the Hinduism, so it has the biggest history. The Buddhism is one of the oldest one, in the sense of you can say in this particular region. So they address this particular question. Okay, when the world will end, and imagine if you have a question, this particular question in front of you, and there are no clocks, there are no time system, there are no calendars, nothing. So how do you answer this particular question? So this is quite a beautiful thing, which was it was believed that there was a tower of Brahma. Now it is in Varanasi in India, but it was destroyed by Tamil. Now it is no more. So according to the legend, there were a temple in the Indian city of Banaras. The temple priests were to transfer 64 fragile gold plates to another tower, and following the same rule of Tower of an Eye. You know, you can't place a disc of bigger diameter on a smaller diameter disc. So it will be, it was believed when the 64 plates were moved from one tower to the other by following the Tower of an Eye method, this world will crumble, uh, the temple will destroy, and everything will crumble into the temple. The whole world will destroy. And let me tell you now, this is the time we can say that how, what was, whether the prediction was good, pretty good or not. So, okay, so if we believe that we are moving the 64 discs in an optimal way, so we know the answer 2 to the raised by 64 minus 1. And if we require only 1 second to perform one disk movement, so it requires around 584.5 billion years. And by the way, this is a very overestimated thing. So now, okay, this is again a prediction of the supernova, the availability of the hydrogen in the sun. You know, there is a fusion process is going on. If our sun is out of the fuel, then definitely everything will crumble. So this particular fuel age is around 4.543 billion years. But I still think this is a quite a beautiful thing that they think of out of the box to predict the age of the Earth in this particular way. Okay, this is again mathematics, mathematics, mathematics. Everywhere they are answering the question of their surrounding the big question. Okay, look at the Greek mathematicians. So if we talk about the history of math, so it can't be done without naming the Greek, bringing the Greeks into the history. So it is Greeks who have given us a formal proof methods, and particularly due to Euclid and the number theory, mathematical analysis, and applied mathematics. I must say that applied mathematics has its root in Greek history. And let's talk about the three important problem, classical problem of antiquity. I told you that one of the problem is there. So you have seen one problem in the Vedas, which was proven that you can always construct a circle of if you are given with the square and they have the same area. But what about the reverse problem of it? And let me tell you that there are certain cases, and even Stephen Hawking in his book, the God created integers, in his book, he had made the case that when Greeks were trying to understand mathematics, so they have learned Sanskrit, they have taken some material from Vedas as well. And they saw that particular problem and they come up with this particular problem. Can we reverse that particular process? If you are given with a circle, with a given area, can you construct a square of the same area? But this time the tool was changed. The tool was not, I think the biggest invention of that time in the geometry was this compass and the straight edge. By using the straight edge and compass, can we do that or not? And the second thing is it possible that for a given unit cube, we can construct a cube which is full of the volume of a given cube? Even with cube is a very, very important thing. So even the other way around is not so easy. If I give you a cube, can you cut it in a way so that you get two cubes? This is an open problem for the participant. And similarly, trisecting an angle. So some angles are easy to trisect. So you can trisect 90 and 30 is constructible. But the question is, can I trisect 30, whether 10-degree angle is constructible or not? So these are the three. And by the way, this particular problem is related to this one, whether certain n-gons are constructible by using the n-gon. And you know, this particular problem was quite in the air at that time. I will explain why. But these are the three problems which were given us to by Greeks as a time capsule. You know, this particular concept is quite important. If mathematicians do live histories, and mostly new theories are replacing the keywords. So keywords keep on changing, keep on developing with paper. Even after 10 years, people are using different keywords to address the same problem, and statements keep on changing, but the questions stay the same. And this particular problem is these three antiquity problems are the most important one. Time capsule is a concept you have to, if you are being asked, you need to send a message to the people who are going to come after 100 years here. So what you are going to tell them about today? So mathematicians think this way, that we need to construct some problem what we can pass on to the upcoming generation. So this is the time capsule what Greek has passed on. And you know how many years mathematicians took to find the answer to this, but these three simple looking problem, 2000 years. 2000 years. People tried to find this construction and failed. Either, so these were the three conjectures, whether this is doable or not. And I think now every student who learned algebra, particularly the field extension, they know that these three constructions are impossible. And these persons have worked. What it was, the first one was the Gauss who gave an answer. So it was, the problem was thought by Greeks. Gauss was the first one who find an answer. Potzel was with the second question, and Lindemann was with the third question. And they show that these three constructions are impossible independently. If you would like to see how algebra come into the play, so I invite you to please read any book of algebra and read the detail how one can relate polynomials and how field extension plays a very important role in answering all these three questions. By the way, what we are studying today in our graduate text, so definitely mathematics of the forthcoming generation is becoming easier. So he basically simplified the proofs what was given by Gauss, Watson, and Lindemann. And this is David Hilbert who unifying all this construction. Now we know that these are possible. These are called the antiquity problems as well, the most famous problem in maths. Okay, let's talk about Euclid. So we are discussing about the Greek era. So Euclid has done a remarkable work. So he has written Elements, the 12 volumes, and he collect all the knowledge of mathematics at that time. And at those particular texts of Elements, it is based on, so he tried to prove all the statement by using five postulates. So the first postulate of the Euclidean geometry is, I hope many of you are already, I'm sorry, I'm boring you, but the first postulate is quite simple. So with every 2 points, you can always find a line segment, and this line segment can be extended to a straight line, which is non-ending. And with every given 2 points, you can always draw a circle. And the fourth postulate is that every two right angles are congruent. And the fifth postulate is that if there is a line, if there is a point, so there always exists a line which is parallel to the given line. So these five things apparently are very simple tools, very simple looking problems, postulates, and I think we have seen these in our school. And what Euclid did, he tried to prove the proof of everything by using the four postulates. And somehow he always think that the fifth postulate is somehow is not a postulate. It need a proof, and he tried, but he could not. So that's why he put it in the postulate, and he avoided it up to 30 proofs, I think. And later on, he started using it. So he leave this particular question to the people who are coming afterwards. So the fifth postulate is the most important postulate in the Euclidean geometry. And let me just tell you, that laid the foundation, that discovery of proving, that quest of proving the fifth postulate was led to a very important discovery. So first of all, meet this guy called Frederick Gauss. And this is a book, it is in German. So there are people who are sitting in German. So Germany, so they can find this particular book. This was written by I don't know Werke meaning in Germany in German language, but this is his unpublished work. So people collected the whole history. So Gauss leave many things uh, at his after his death, and among those particular things, he was trying to prove the fifth postulate by using these four postulates. And let me tell you that fifth postulate is unprovable. No one can prove it now. And this is one thing Gauss was trying to do. And very few mathematicians, young mathematicians, you never heard about Farkas Bolyai. So he was a friend of Alfred Gauss. I know I didn't put Riemann in this story because I want to give an essence how this theory of non-Euclidean geometry originated. Riemann was a very important figure in this particular story. But at that time, I just tried to give a sense of how the things were, this problem was attached to the life of the people. Gauss wrote a letter to Farkas Bolyai in 1779. I have indeed yet ever that hope, the hope that those rock sometime, and indeed before my end, will allow a through passage. He was trying very hard to prove it, but failed every time. Hannes Bolyai, he ruined his life. It was in his whole life, he worked on one major problem, and that problem is proving the fifth postulate of the Euclidean geometry. So Janus Bolyai work was, anyways, he published ultimately a book in 1832. And in the appendix of that particular book, there were a few pages of his son, Janus Bolyai, and Gauss comments on Janus Bolyai's intelligence is that Gauss, on reading the appendix, wrote that I regard this young geometer, Janus Bolyai, as a genius of the first order. And when he was very, very young, and later on, now you can see the conversation between the father and the son. A father who lost to a problem, he is advising his son, for God's sake, I beseech you, मैं मिन्नत करता हूँ for Urdu people, मिन्नत करता हूँ to give it up, not waste your life in proving the fifth postulate. I wasted, or I fear it is no less than a sensual passion because it too many take all your time and deprive you on your health, peace of mind, and happiness in your life. So he was warning that the advice was quite bold. So you can search that advice on Google, and in the beginning it was very bold. So I tried to water it down. So he used very harsh language to warn his son to not work on the fifth postulate. He was defeated badly, and Farkas Bolyai was quite disappointed with his life. Probably in the beginning, if he would not be attached to this particular problem, he would have done something so that the forthcoming people would know him more. And then he was having the same fear that probably he is a defeated mathematician, so his son would have the same for fate. But this is really important. He has written, you know what was written in this appendix? It was his thoughts on parallel line concept. So the concept on parallel lines, and someone read this particular appendix, and it was a Russian person. His name is Lobachevsky. In 1848, he published his paper, a piece of work similar to his appendix in 1829. And the appendix was in 1829, and he has written the paper in 1848. And to Lobachevsky's work, so again, Jason Bolyai, he sees that, oh, this goes now. And he says that basically this problem is not doable, but we do have surfaces where Euclidean geometry doesn't work. And Bolyai and Lobachevsky pioneered the investigation of non-Euclidean geometry. Particularly, this was the birth of hyperbolic geometry, those people who are familiar with. So he wrote to his father, my dear father, good father, I have so much to write, my new creation. It is at the moment impossible for me to enter into great deal, work on parallels. At this moment, it is not yet finished, but the way which I have hit upon promises me with certainty attainment of the goal. If it is in journal attainable, it is not yet attained. But I have discovered such a magnificent thing that I am myself astonished at them, and it would be damage eternal if they were lost. When you see them, my father, you yourself will acknowledge. He was out of excitement. The paper was not out. He was sharing his feeling with his father. And by the way, all these excerpts are taken from this particular book. So this book is, I think, available, and this book contains the collection of letters what Gauss was writing to the mathematician, and particularly Bolyai family. They are Hungarian, and they are mainly responsible for the propagation of the work of non-Euclidean geometry. One of the very greatest discovery in mathematics since ever the world began is the non-Euclidean geometry. And by the way, here we surpass the Greek era. So Greek era ends here. From here, non-Euclidean geometry is non-Greek era, I can say. But I must talk about Archimedes. Archimedes was, okay, people might know about the field medal. So in the field medal, there is a picture of only one mathematician. And that mathematician is Archimedes. Archimedes is very special mathematician in many ways. And he was not only a mathematician, he was a great inventor as well. People might heard of his story of Eureka. I didn't have time to explain because I am already on overtime, closing time. So this is a story where Archimedean principle in fluid dynamics is very important, where you know about some objects float on the surface and some really sinks. So what is the reason behind it? Then he was a protector of his city, Sicily. So it was attacked by the Romans, and he built this Archimedean cloth and burning lenses and Archimedean screw to drill the water to 200 feet. And and this is the most important thing. Old people were were quite conscious toward the tombstone. So what will be there written in their tombstone? And by the way, in the field medal as well, on one side you can see the picture of Archimedes. On the other side of the field medal is this thing: relationship between the volume of the sphere, cylinder, and the cone. And among all these pictures, no picture can match the importance of this particular picture. So, Archimedes has already found the crux of calculus. So he tried to understand the importance to try to measure pi. In order to measure pi, he constructed a method which is known as the method of exhaustion. And this method of exhaustion was used for many years until unless Newton came up with the fundamental theorem of calculus to find an answer to area problems in mathematics. This was, many people believe that this was the birth of calculus, and it is again coined after Archimedes as well. And during the same time, Zeno gave us paradox. People were talking about the concept of infinity. Uh, you might heard about George Cantor is named as the father of set theory. Before George Cantor, what mathematicians used to believe? They used to believe the concept of infinity as potential infinity. And who gave the concept of potential infinity? It was no other than Aristotle, who gave that. And all these debate was started with one paradox of Zeno. And paradox is quite simple. If you have a runner, fast runner, and if you have a tortoise, and now you have to follow one rule. I'm saying you, what Zeno's told us. Okay, allow the runner to occupy the position of the turtle, and then during the same time, the turtle should be allowed to occupy the new position. Okay, and again, Archelaus, runner, allowed to occupy the turtle position, and the interval of time, the turtle should be allowed to move, so it will take a new position. If you are moving in this way, so the runner, Archelaus, can never catch the turtle. The process will keep on going. Those people who are more interested on applied side, this was a serious challenge to time and space problem. And people were trying to understand. And this was a problem which lead the philosophical discussion on the concept of infinity. And it leads to a particular series at that time, which was giving you the answer one, the Zeno's paradox, and the entrance was going to infinity. At that time, this was a huge, non-understandable thing. And Pythagoras was also a musician, so you can search for music of the Spheres by Pythagoras, and same thing is being used. So January, February, the month with 31 days and 30 days. So the same thing is Pythagoras, Sphere, and Roman was okay. A Roman warrior Julius Caesar. The month of July is named after him due to one important reason because he was one of the greatest Roman leader and he created cipher. So the coding theory started with the work of Julius Caesar. So Julius Caesar cipher is the first coding mechanism we had in the history. And in the Middle Ages, there are many things. So I invite you to look at Khayyam method, how he was using the cubic, he was using circle and parabola to solve cubic equation. It is very interesting, very enriching. And I think Al-Khawarizmi is well known to everyone. The story of circle, it is very close to the heart of engineering sciences. And then these kind of sequences. But the most important thing, I think very few people know about amicable numbers. And amicable numbers were again known to Pythagoreans at the time. So let me just tell you, what is this amicable number? So if you factorize 220 and you add its factors, you get 284. Now you factorize 284, you just find all factors of 284, you add them together, you will get 220. So this is quite an interesting work. And by the way, during his lifetime, Pythagoras were able to find probably the only pair. Pythagorean believe that there is only one pair of amicable number. But there was a person, Tehbat ibn Qura, I wrote his name because I always forget it. He is an Iraqi mathematician. You know what he has given? He has given an algorithm to build these amicable numbers. And this is around 850. And amicable numbers are now it has many applications as well in computer sciences. But the application is not important. problem is very important to look at how to construct, find more amicable numbers. So you can know, by the way, no video by number file. Mathlogger has been made on addressing amicable numbers at the moment. So particularly a motivation for the ones, maybe this is a lost thing. I think Renaissance era was quite important for the people who wanted to know about binomial, the work of Italia. There's a lot more story, interesting stories, but I think I'm already over time. But hey, this is very close to my heart. Tolstoy versus Poincare. So he's a Russian philosopher. This is our Henry Poincare. So Tolstoy was a philosopher. He once write that explains somewhere in his writing why, in his opinion, science for science sake is an absurd conception. We cannot know all the facts since they are particularly infinite in numbers. So we must make a selection what to study and what not. So according to Tolstoy, he said, is it better to be guided by the utilities that we study only those things who has application by our practical and more especially moral necessities? So this was his philosophy that scientists should study or mathematicians should study only those things which has application. And you know, this writing was responded by this man, Henry Poincare. This is the title of, say, Apology for a Few Fools. Scientists believe that there is a hierarchy of facts, and that is a judicious. And then you can read more. I can share the slides. And he was very harsh at Tolstoy. And he said that if mathematicians from the beginning they thought of mathematics in this particular way, so no mathematics would exist, no application would come into existence. And this is a complete, and for the audience, I just let you know that you might heard of the famous book of Hardy, Apology of a Mathematician. That particular word of apology was inspired by Apology for a Few Fools, by already written by Henry Poincare. And the same thing was mentioned by David Hilbert in his farewell speech. So this is a very famous incident in the mathematical history. It's close to the heart of many mathematicians. And being a young mathematician, you should read about Tolstoy versus Poincare. Just Google it. The whole essay will come in. So you will read the Tolstoy point of view and then later on response of Poincare, the full. A mathematician who saved millions of lives, what mathematicians do. So anyone can read about Alan Turing. He saved millions of lives. This is a pity that we are again going through a war era. But now, again, this is not the scenario, but definitely in future, quantum computers are going to play a very important role. And in the last, oh, I can skip this slide. It requires a lot. So this is always a component of my talk whenever I speak. So book recommendations previously. So this is a book, Living Proof. You can't learn mathematics with every mathematician has a story of resilience. They had gone through a rough phase. So Mathematical Association of America collected such stories of resilience. And this book is freely available. You just Google Living the Proof, the stories of resilience, you will get it. The most beautiful book is Mathematics for Human Flourishing. I will say more about it in the closing remarks. This is the book of Stephen Hawking. Okay, Stephen Hawking tried to give a historical account of the development of mathematics. This is not a friendly user version, so it is particularly for mathematicians who would like to know about the history of math along with the rigor mathematical facts. And this is the one which is very important. Particularly, this is talking about the birth of calculus, particularly, and why calculus is so important. So even calculus is so vast. I didn't talk about Newton. I didn't talk about anything about calculus, but this book has very exciting stories, very interesting stories about calculus and these things. So Francis Su is a very important character. He was president of Mathematical Association of America. I think in the history of Mathematical Association of America, it happened only once that a speaker gave a talk and the whole crowd stand up and give the standing ovation. And it happened with Francis Hu. You can look at this particular video of Francis Hu. The lecture is quite beautiful, and there is an article, Quanta article, about the same lecture. So this happened also only once that someone has given a talk in the final meeting of Mathematical Association of America, and later on Quanta has written an article on. And you know what Francis has given? So he said that the ancient Greeks argued that what are the component of the best life? So they reached to a particular conclusion that beautiful the best life is life which has some beauty, truth, justice, play, and love. These are the four, one, two, three, four, five. These are the five important components: beauty, truth, justice, play, and love. And all these components, he made a case that in this book, Mathematics for Human Flourishing, he made a case that math has all these components. And in the beginning, he told a story of a young man who was convicted for lifetime imprisonment. So he was sitting in the jail and he wrote a letter to Francis Hu. I messed up with my life. Now, rest of my life, I have to spend behind the bar. What should I do? How I can see value in my life? How I can bring some value for myself? So he started studying mathematics, and he was keep on sending him. Okay, he covered calculus, then algebra, then other things, and that was a central character of his book. And later on, I think if you watch his lecture, you will find everything. And this is the final message by Francis, so not by me. To live your best life, do mathematics. That's it. Thank you. Thank you for your patience.
Yeah, thank you very much, Imran, for this interesting and engaging talk. So in the audience, if somebody has comment or question, please go ahead.
There are something in the chat.
There are the compliments that
Oh.
you receive, yeah.
Okay. I do understand. So a speaker should take it. A negative. There are no, there are no so questions. No, this is not a research talk. This is a story kind of a thing. I can understand.
I think it was really motivating how the mathematics evolves. Yeah. Do you have a question?
Anyone has a question, and feel free to write me if you need to discuss anything interesting or need to know more.
So, Izhar, please go ahead.
Izhar, go ahead.
Okay, so, okay, please unmute. Oh, he's muted. Sorry for that.
Assalamu alaikum.
Walaikum assalam, Izhar.
How are you, everyone?
I'm fine. Thank you.
Okay, I'm throughout the talk. The talk was really nice. So since the history of mathematics is so rich, so it's quite interesting that you have collected I think all of the history in a 1 hour talk. So that was quite informative. But throughout the talk, I was just trying to do something on the page where the first three problems that you wrote. So if we can please go to the first three problems. I was trying here on the page, so I thought I have missed something on the problems. So if we can discuss it. This problem says we can go up to the diagonal and don't we
Yeah,
cannot
you can't.
cross it.
Yeah, you can't cross a diagonal.
Okay, so how many ways are possible here?
Yeah, if the grid
Yeah.
is by n by n. So this is for 5 by 5, I think. 4 by 4.
So if we take a 3 by 3 grid,
Yeah,
so
you can start with 3 by 3, even 1 by 1. So there is only
only
one
one
way.
path, one way.
Yeah.
Now
Then 2 by 2.
I took a 3 by 3 grid. So what will that correspond to in the next problem? Okay,
So
that will correspond
okay,
to.
it can be seen through this particular thing. So this parenthesis can be for right, and this
Uh,
parenthesis the other one can be for up.
okay,
So
if there are
whenever you want, so there can be many left brackets, so that means you can move horizontally. But for the upward, you can't put an extra parenthesis if there is no one here. You
now I
understand?
want to understand this problem. We have to group two at a time, or there is no restriction like that.
Oh,
If
sorry.
for example I write if there is a 3 by 3 grid,
Okay,
so
3 by 3 grid.
how many symbols do we take there? There is no restriction of symbols.
Symbols mean the parentheses you are saying. So it means three
For
pair
example,
of parentheses. Three pair of
no,
parentheses.
I will take a product of A, B, C, D, and E. Is it the way we will?
Okay. So you are trying to. Okay, you are trying to record the path, as I understand. So A, B, C, D. You mean you are trying to record the path A, B, C, D.
Yeah, so that we
So
can
the best way to record it is just moving for up. You can use U for instance for this particular path. Okay, this is an interesting question. Let me just use the annotation. Am I allowed to? Oh, here is the annotation. There are no. I can't annotate. Um,
I can
okay,
understand if you can
so
tell me
try
like
to
that.
understand. This is right. This is R. This is
A,
U. This is R.
R,
R. R. U. 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 This is one path. For the other
okay.
path, this is R. R. U. R. U. R. U. U. This is the second path. Instead of using
Okay.
A, B, C, D, E, F, so it doesn't, uh, you cannot record the paths. The best way is using R, right, and up, U. R, U, R, U. Got it?
Yep. And we
Okay.
can't come down again.
Yeah,
There is
you are very, very consistent, mathematician. I like your attitude always.
okay. And what's in the middle one? Please explain to me.
Yeah. This is the same. Oh, for the middle one.
The second,
This
the
is the
second
hardest
problem.
problem. This is the hardest one. Okay, how to connect this thing with the parentheses and with the that requires a big proof. That is not so that is not so trivial, and probably I cannot explain it right now.
Okay.
So, but
And for a three,
I will send you the correspondence between the two. But
yeah,
this
it
is something
seemed
I don't know at the moment.
it looked quite interesting that you said that these
Apparently,
two are
yeah.
connected.
Apparently, it
Yeah.
does not. Yeah. Apparently,
So
this is the most classical one, and apparently these two are not connected. Apparently,
during the
so
whole talk,
connection.
during your whole talk, I was writing here on the page. I could connect the first and the third, but I was unable to connect it with the second one. So I will
Yeah.
think. Okay.
Yeah. I will send you the proof how this problem connect with the previous one. By the way,
And
there is only one graduate text, the Book of Stanley, what I mentioned, and we have done one math circle for